Let us start lecture 11, and the course is phase diagrams in single component and binary systems. What we have done till now, we have been trying to understand equilibrium, and later on you would see that this equilibrium consideration would be required to understand the equilibrium between different phases that can appear in a single component or multi-component systems. And in fact, we will be limiting our discussion in binary systems, but those equilibrium conditions should be understood first. That is what we have been spending a lot of time to understand equilibrium. So, the today's topic is, it is basically the concept of equilibrium will continue, and on the basis of auxiliary functions now. In fact, last class we have understood the importance of auxiliary functions, because these auxiliary functions, which is Helmholtz free energy and Gibbs free energy, which is G. So, these two will be dependent on some independent variables, and those variables would be convenient to measure at the same time control, and that would define the state of a system or equilibrium of a system. So, these are the topics, two topics we will consider, and let us just list down what we have done till now. Okay. So, exerts if you want to know. So, few points. From discussion till now. If I try to look at, so one is entropy of a system increases. Just let me write down. We can say this as natural or spontaneous process. Second is entropy is a state function. Third is under reversible condition, entropy cannot be created, rather entropy transfers one place to another, and that is what del S total equal to 0. We have seen that delta S total equal to 0. Okay. Or in other way around, we have seen a more specific expression, if we want to see, equal to 0. Fine. That is what we have seen. So, in fact, taking the clue from here, del S under constant internal energy and volume, that is 0 for reversible situation. So, from there we can also get an idea of equilibrium. So, equilibrium idea, equilibrium understanding rather, it gives you the entropy of an isolated system goes maximum. Okay, so, that time it becomes equilibrium. Similarly, same equilibrium condition would be internal energy. So, I can say this is as SUV condition goes to maximum under equilibrium, which is constant internal energy and constant volume, and here del u s it should be 0, and that time okay. So, it is basically constant entropy and constant volume, and then u should go to minimum. Okay. So, that is the equilibrium condition what we have seen. Now, if I try to look at this from the understanding of that evaporation case of 1 mole of liquid to 1 mole of vapor. So, therefrom we can actually say this. So, let us look at that a little more. So, we know that delta S system equal to, this is a general expression, plus delta S irreversible. So, this is in the case of, we have seen the last in the lecture 9 as well as lecture 10, we have seen that. So, this is coming from the experiment what we have conducted, which is irreversible evaporation case. So, now I can write this as Q can be written as del U plus W divided by T plus del S irreversible. So, this is actually coming from, if you recall, del S system equal to Q by T plus Q reversible minus Q by T. So, from there we get this expression. So, now it becomes, so I can write it as T del S system equal to del U plus W plus T del S irreversible. Now, if I take this in the form of constant, if we take conditions. So, if we take condition constant U as well as constant V, and if we consider only mechanical work, so if constant volume, that means mechanical work would be 0. So, I could see that T del S system under constant U and V condition would be equal to, so this goes to 0, this goes to 0 because constant U and constant volume. So, this becomes delta T delta S I irreversible. I can, this T is a finite quantity, so I can, it is a non-zero quantity, so I can cancel. So, then I can see that del S system U V equal to delta S irreversible, or in the differential mode okay. Now, this is the situation where we have irreversible situation, and this quantity is always greater than 0. Delta S system U V greater than 0, and this is 0 when it goes to equilibrium. So, del S system equal to 0 when equilibrium. So, this is for irreversible. Okay. So, that means it is very clear that when the irreversible process happens, under constant internal energy and volume, the system entropy goes up, and at some point of time when it reaches equilibrium, rather when it is starting to reach equilibrium, the degree of increase of entropy gradually goes down. So, it is basically, if I try to look at the entropy variation, let us say I have A plus B equal to C plus D, this reaction is taking place. So, this side is A plus B, this side is C plus D, and here we have composition. So, I can see that the entropy would be maximum at some point. Okay. So, here we have maximum, okay, and that will be the equilibrium composition. And what I have said, that the degree of increase of entropy as it approaches equilibrium, and here this axis is entropy, okay, approaches degree of increase as it approaches equilibrium would reduce. So, if you see the slope is gradually reducing, both the sides, if you start from C to D or A to B, both the sides you see as it reaches to this peak, the degree of increase of entropy reduces, and then finally at this point I could see the slope becomes 0. So, this is 0. Okay. So, that means, so this is the condition we are getting when it is under constant internal energy and volume. The similar can be proven for U. Okay. See, if I take this equation again, so I can write this equation as del U delta U equal to T delta S irreversible plus, or I would say minus W minus, it should be delta S system T minus T delta S irreversible minus W. So, this goes to 0 if we consider the similar condition, which is only mechanical work, volume constant and only mechanical work. So, that time this work component becomes 0, and if we take these two terms, so these two terms becomes like, so this is the term which is positive always, and this term, depending on the situation of reversible or irreversible process. So, this is this. Now, I am taking assumption, another assumption, let us say constant entropy. So, that time this is system entropy. So, if I take system entropy, so that time del U, this should go to 0 constant. So, S V should be equal to minus T irreversible. So, that means if there is an irreversible process, the internal energy under constant entropy and volume should go down, because this is positive and there is a minus sign. So, it should go down, and when it reaches equilibrium, so that means del S irreversible equal to 0. So, then this goes to 0 or less than 0, because this is irreversible case, this is reversible case, reversible case. So, I can write less than equal to 0, fine. So, that means when irreversible process takes place, in this case U goes down, and in this case U must have reached minimum value, because as it is going to achieve equilibrium, the internal energy decrease should be the maximum. But internal energy decrease, I am talking about decrease because it is going down. So, that means internal energy should reach minimum. So, here minimum value. So, that means this is also equilibrium, so it is a reversible, that is what it is, equilibrium. And here if you see, this is equilibrium. So, we started with this statement that equilibrium understanding. So, now we could see from the equation we can actually prove that. Now, finally, we got one more information, we got 5, that is convenient choice of independent variable. So, what are those independent variables? P, T and V, these are the convenient choice. And in what case? Closed system, fixed composition. Okay. So, this condition I should have these 3 parameters which are very convenient. So, why I have said fixed composition? Because once the composition changes in closed system, or if it is open system where the mass can actually exchange with the surrounding, then definitely we need to incorporate another variable which is composition. The composition can be included in the form of moles of different constituents or components that are present in the system. So, those moles will also be a kind of convenient variable, because I can count that, fine. And here all those 3 parameters will be easy to measure and control, even the moles, number of moles in case of open system or a closed system where reaction is taking place and composition is getting changed. Okay. So, we will come to that part later, but first let us look into this. Why we needed this? Because we know that S entropy can be function of UV, internal energy can be function of SV, and here if you see U and V are the independent variables. V is still easy to convenient way to measure and control, but internal energy is a difficult proposition. Similarly, in case of U, S is a difficult proposition or inconvenient choice of independent variables, but volume is definitely convenient choice. Okay. So, now from there what we have understood, that we need to bring in auxiliary function. Auxiliary function, what are those? Helmholtz free energy, which is termed as A, and Gibbs free energy, which is termed as G. Okay. And we will see that A is reflected in this pattern, or I can write Ts, and G can be written as. Okay. And this 2 equation can take us to, let us look into this too. So, these 2 equation can actually define the equilibrium of a system as a function of Vt and this one as a function of Pt. So, that means those are easy choice of or the convenient choice of independent variables. So, in fact, what we see that we have to see whether U is Helmholtz free energy is dependent on pressure, volume and temperature, as well as Gibbs free energy is dependent on pressure and temperature. If I try to look at, so we can see like this. Let us consider system is changing from 1 to 2, this is final, this is initial. Okay. So, now I can see this is A equal to U minus Ts. So, I can operations here. Okay. So, this is state change that is taking place, and I can write this fashion. So, this I can write it as du can be written as del q minus del w. So, which can be written as T del S minus P dV. So, this becomes T del S minus P dV minus T del S minus S dt. So, these two terms can get cancelled. So, I would get an equation like minus P dV minus S dt. So, hence I would see that A is a function of V and T. So, that means I can actually, this is a free energy term which can be defined, which can be changed by convenient change in volume and temperature, and we will see that this A is also a state function, and A minimization, the minimization A of A in A rather would dictate us the equilibrium. So, and that is what the equilibrium can be explained on the basis of a convenient choice of independent variables. Similarly, if I try to, so this is with respect to Helmholtz free energy. So, if I try to look at Gibbs free energy, so I can again state 1 to state 2, G equal to H minus Ts. I can write it as delta H minus T del S minus S dt equal to H equal to U plus PV. So, I can write dH equal to du plus PdV plus V dP. So, then it becomes du plus PdV plus V dP minus T del S minus S dt. Okay. So, I can see that this term is nothing but, since we know that from here, if I know, so du plus PdV equal to T del S, from here I can get. So, I can convert this one to T del S plus V dP minus S dt minus T del S. So, I can cancel this. So, it becomes V dP minus S dt. So, G becomes a function of V, P and T. Okay. So, like that we could see that with the free energy term can be defined with the help of convenient choice of independent variables. We will treat these two free energies in order to see the condition of equilibrium, because the condition of equilibrium with the help of minimization of internal energy and maximization of entropy, those are not very convenient way of deciding the equilibrium state, because that is decided by the inconvenient choice of independent variables. So, in the next class we will try to look at how this A as well as G, which is two free energy terms which are auxiliary functions, can decide the equilibrium definition of or equilibrium condition of a system. Thank you. So, we will continue our discussion on this very topic in the next class. Thank you.